We'll practice applying conservation of energy to beta decay and see how the neutrino was predicted. Here's the problem. In the beta decay of a stationary nucleus, the total energy released, called the Q value, is 0.80 MV. In a particular event, the emitted electron carries 0.30 MV of kinetic energy, and the heavy daughter nucleus recoils with negligible kinetic energy. Part A. Show that energy appears to be missing if only the electron and daughter are produced. Part B. Determine the energy that must be carried away by a third undetected particle, the neutrino, and express it in joules. First, let's account for the energy if only the electron and daughter are produced. The energy released should equal the kinetic energy of the electron plus the kinetic energy of the daughter nucleus. The electron's kinetic energy is 0.30 MeV, and the daughter's is negligible, so the total is about 0.30 MeV. But the Q value is 0.80 MeV, so 0.50 MeV is unaccounted for. This shows energy is missing if only two particles are produced. Conservation of energy requires a third particle. The neutrino's energy is the Q value minus the kinetic energies of the electron and daughter, so the neutrino energy is 0.80 minus 0.30 minus 0, which equals 0.50 MeV. Now convert to joules. Recall that 1 MeV equals 1.6 times 10 to the minus 13 joules. Multiplying 0.50 by 1.6 times 10 to the minus 13 gives 8.0 times 10 to the minus 14 joules. The continuous spread of electron energies, rather than a fixed value, led Pauli to predict the neutrino to conserve energy and momentum. So the missing energy is 0.50 MeV, which is 8.0 times 10 to the minus 14 joules, carried by the neutrino. In beta decay, the continuous electron energy spectrum reveals that a third particle, the neutrino, must carry away the missing energy to satisfy conservation laws.